participar y acompañarnos en este importante evento. Un aplauso y demos inicio. Muchas gracias.
Muy bien, brevemente comentar que el doctorado en Ingeniería está en su 5º año de configuración, que tenemos 9 egresados, que estamos en inscripciones que ya están cerradas para el año que viene. Tenemos cerca de 25 inscritos y que es una apuesta al quehacer de la Universidad Distrital, apuntando al desarrollo y la construcción de conocimiento y generación de nuevas oportunidades de investigación en nuestro país. Bien, pues bienvenidos al segundo workshop para el doctorado en Ingeniería de la Universidad de Francisco José de Caldas. Es un motivo de orgullo y un honor contar con su presencia en este evento, orientado a toda la comunidad interesada en los temas de computación de alto desempeño, su presente y su futuro. Agradecemos enormemente su participación e interés en las temáticas que en esta ocasión hemos querido presentar. La conferencia de apertura que tendremos a continuación, AWS Cloud Service for Research Computing and HPC, estará enfocada a las capacidades de Amazon Web Service para hacer la computación científica accesible a toda la comunidad, así como nuevos enfoques de computación de alto desempeño. El conferencista invitado, el doctor Kevin Jorissen, líder de desarrollo en investigación y computación técnica de Amazon Web Service. El doctor Jorissen cuenta con un doctorado otorgado en la Universidad de Ashburn en Bélgica y trabajó como investigador postdoctoral de la Universidad de Washington en Tirol, la Escuela Politécnica Federal de Lausanne y la Universidad de Zúrich. Tiene 10 años de experiencia en ciencias de computación. Como físico, el doctor Jorissen desarrolló programas que resolvían las ecuaciones de física cuántica que describen los fenómenos de absorción de la luz en materiales. Su trabajo ayudó a mejorar los cálculos teóricos de la absorción de rayos X, así como la espectroscopia de pérdida de energía de electrones. El doctor Jorissen ha dictado workshops a través de todo el mundo y fue usuario pionero de computación de alto desempeño en la nube. Esta combinación de mejor software, enseñanza y acceso a recursos de computación en la nube habilita a que los investigadores y científicos puedan realizar simulaciones de vanguardia de sus investigaciones. Debido a ello, el paso natural del Dr. Jorissen al afiliarse a Amazon en 2015 para ayudarlo a acelerar la adopción de la nube dentro de la comunicación científica global. Como parte de su trabajo, el Dr. Jorissen se relaciona con científicos de varias disciplinas, representantes de AWS, en alianzas de academia e industria tales como RaceLab de Berkeley, Big Data on Job de la Fundación Nacional de la Ciencia de Estados Unidos, y es el responsable de proyectos como el manual de AWS para investigadores y el Global Data English Bible for Research. El Dr. Jorissen es traído al evento gracias a Amazon Web Service. Agradecemos las incansables de gestiones del Dr. Carlos González Villegas, presente aquí, gerente regional para la América Latina en las líneas de gobierno, educación y negocios, sin ánimo de lucro. Amazon Web Service y su equipo de trabajo, muchísimas gracias Carlos, muchísimas gracias Dr. Jorissen, y pues Dr. Jorissen will come to Colombia. It's a pleasure to have here with you. I think the audience is unexpected.
Thank you very much.
Esta conferencia está siendo transmitida por streaming por la red RITA, la red avanzada de telecomunicaciones de la Universidad Distrital. Y pues sin más preámbulos, un fuerte aplauso para el Dr. Jorissen.
Very good morning to you all. Thank you for being here. You've already gotten a long introduction to me, so I won't repeat it here, but you can see a silly photo of me at the synchrotron in Beijing. So the goal of the talk today is for you to understand what benefits the AWS Cloud can bring to your HPC work, to understand the things that are new about doing HPC in the cloud, that are different from how you may have done HPC in the past, and hopefully you will go home with enough confidence to go to the AWS website and maybe give it a try for yourself. And the talk is going to follow a very traditional outline. We start with some introductions, then we start with the traditional HPC stuff. Let's do an HPC cluster on AWS and see how well it works. And then we will move on to more exciting new things like serverless computing or machine learning. And we'll have some words specific about the research community at the end, because of course you here are all researchers. So let's start with the basic building blocks. This is mostly for those of you who are not yet very familiar with cloud. Those of you who are more experienced, just give us 10 or 15 minutes to catch up to you. So high performance computing is a word that contains many different types of work. It goes from work with very light input or output data requirements to work that is very heavy on data. And there is work that is very tightly coupled, where the compute elements have to communicate very intensely at low latency. And then there is work that is much more loosely coupled and that can be executed on a grid. And all the domains of science fall somewhere on this graph. Now HPC, high performance computing, is actually an evolving concept. If you think about it, there we go. From the first computers, we moved to supercomputers, then Beowulf clusters came to be, and then for the last few years, cloud is the exciting new thing. But the technology also evolves. These days you see GPU accelerators everywhere, there's Internet of Things and Intel SGX and exciting new things. The applications evolve. It used to be that everybody ran a big Fortran code with NPI, and these days people try to break things up in small pieces and do microservices where possible. Or the data becomes so big that the data is the thing that has the gravity, and the simulation has to come to the data. The users also evolve. These days, I have friends who do high-performance computing in linguistics or economics. That was unheard of 10 years ago, but it is normal today. And these new users have different skill sets and different expectations than the old-fashioned users like me, the physicists from work on code from 1970. There is already a lot of high-performance computing happening on AWS. So AWS is very big. We have millions of customers. And if you ask, can I do X on AWS? Probably the answer is somebody is already doing it. And so you see there is weather simulations, genomics, molecular dynamics, and whatnot. We're also present in high-performance computing by contributing code to important open source initiatives like OpenAPI or Kubernetes. And we keep investing also in the hardware. So every year we'll have a new type of server that's faster than the year before. Every year we improve the latency and the bandwidth of our network and so on and so forth. So how is cloud computing different from on-premise? On-premise means you buy the computer from Dell and you put it here on the campus and you take care of it for the next 3, 4, or 5 years. So instead of doing that in the cloud, you request servers by the hour. You say, I want 10 computers for 3 hours, and then I don't want them anymore. You access those servers over the internet. So it's like using SSH to connect to any Linux server that you know. You pay just for what you use. So HPC, roughly, you pay per core hour. And most importantly, you let AWS do all the boring work and do it well. So AWS installs the hardware, takes care of the cooling, the power, replaces the hard disks that fail, resizes databases, and all those things. You don't need to do that anymore. And the benefits of this are fairly obvious. So getting servers by the hour means that you can use something different today from tomorrow. Maybe today you need 1 GPU, tomorrow you need 1,000 CPUs, so you can easily do that. Pay for what you use means that you never have to spend money on idle computers that aren't working. So every dollar is spent in a useful way. And letting AWS do all the boring work means that you can focus on science. When I was a graduate student, I had to repair our old cluster down the hall. This was not very interesting. and it did not help me graduate any faster. So you don't have to do that anymore. And the campus IT specialists can put more of their focus on actually working with the scientists. Less time with the racks and the disks, and more time helping the scientists architect new compute solutions. So this is also very exciting. You may have heard about public and private cloud. So public cloud, it's like AWS. It's very big and anybody can go there. Private cloud is that you have your university computing center or the government center and you operate it like a cloud, but it is on a smaller scale. What you get with the public cloud, the scale is so incredibly large. We can, for example, go to Intel and ask for a custom processor, and they will make this for us. We have capacity so much that you will never run out. It's not like you all need to go to the same conference and everybody needs to compute at the same time, because we are just so much bigger than that. We have data centers all over the world. So if you have a collaborator in Brazil or in Japan, that's fine. We can support those collaborations. We invest more in security than anybody else. And we have not just servers, but we have 100 other services to do machine learning or data analytics or make the most off of your science. And we just work and improve on those at a pace that almost nobody else in the world can keep up with. And just to drive home the point, we had a discussion recently with a government agency somewhere else in the world that had a few $1 billion and wanted to build its own cloud. And it turned out, even with a few $1 billion, you cannot do this. So you need to come to the public cloud to really have all the benefits. Now there are, excuse the typo, there are several public clouds, right? AWS has sort of, we think, it distinguishes itself by having the longest experience, the widest array of services, and it's also deeply invested in research and education. So let me drive home this point again about the elasticity. So if your needs for servers go like this, you can follow that exactly in AWS. Here you have a big experiment, no worries, you just get more computers that day. Here you have a really big idea, and you need to do the biggest simulation of your whole PhD, fine, just get a bigger cluster for a day, right? So you are not constrained in the science that you do. If, however, you have just one cluster with 50 nodes or 100 nodes, then that is the limit. And so here, when you wanted to use more computing, it's not there. So you have to slow down in your work, you have to wait longer for your results, or even worse, maybe you cannot do it. In my field of solid-state physics, to get an accurate result for a material simulation, you needed to describe it with a lot of atoms. The more atoms you could have in your simulation, the more accurate the result. But if your cluster was small, you could not do that, because the simulation would not fit in the cluster. So you were limited also in the science. When you have elasticity, and you can scale to however many servers you need, then you can think, how big does the molecule have to be? And you do it at that size. So it's a real advantage. Okay, so very quickly, so AWS has regions in many places around the world, about 15 or 20 currently. And if you look at, say, just one of these regions, then inside that regions are still different locations. These are maybe 50 kilometers or 100 kilometers away from each other. They're fully independent. And inside each of these locations are several data centers. And so when you run your simulation, you will be in one of these data centers. And then inside the data center, what you do is you say, give me one server, one virtual machine, or maybe give me 3 or 100. And you tell AWS what that machine ought to look like. You give it a virtual machine file. For example, you say, give me Ubuntu Linux. And then it gives you 3 Linux servers with Ubuntu Linux. And then you can connect to this server with SSH, go inside, install your molecular dynamics code, and run jobs. So that is the basic mechanism. Let's look at the building blocks of the cloud quickly. So first we talk about compute, the most important in HPC. So we have different types of servers. And you can tell us you want a memory optimized server or a compute optimized server, or maybe you want GPU. I love this one. C4 is my favorite type of server. I use it every day. And for example, if we look at the C4, we see it comes with, for example, 60 gigabytes of memory, and it has an Intel Xeon processor underneath with a clock speed of 2.9 gigahertz. Okay. And so there are many different types, and you choose the one that's best for your job. And then you can say, give me a whole C4 server, or give me a smaller virtual machine, depending on how much power you need. And we denote that with sort of t-shirt sizes, small, medium, large, extra large. And it goes up to like 8 extra large or so. Maybe it's no longer a t-shirt size at that point. Here's a different way of looking at the same information. For example, here, if I take this server type, I will have 8 CPU threads and 16 gigabytes of memory. And so there are different types to choose from. Now, storage, you have data that you will need to store. I'm going to start from the right. Amazon Glacier is our long-term storage, our cold storage, where you put data that you will not need frequently. It's very cheap, it's very secure, it's where you store the outputs of your project in case anybody ever needs them. Amazon S3 is the general storage. Most people work in Amazon S3. If you're not sure which storage to use Amazon S3. This is extremely secure, almost impossible to lose data, and it also has a lot of added value. Data in S3 is ready to be shared immediately anywhere in the world, with anybody in the world. And that data can immediately be accessed for HPC computation, for machine learning, for SQL queries, and for many other things that AWS offers. That's very powerful. But it is an object storage. So it is just storage, just your files sit there. It's not immediately attached to a computer, to a server. EBS, block storage, is the hard disk. So when you make a compute instance, you're typically going to take a storage disk and attach it to that compute instance. And that's where your scratch base for your simulation is going to be. The temporary files are going to live there. And then for the longer term, you're going to stage them out to S3 or Glacier. We will see this again. Oh, actually, we'll see it right here. So let's say again that you have this virtual machine image of the Ubuntu Linux. You've created 4 live servers off of that. You now have 4 Ubuntu servers that you can use to work. You're going to take a solid-state disk or a hard drive and attach it. This is your working storage. This is where your simulation creates its temporary files. And then for longer-term storage, you will store output in the S3 storage, from where you can download it to anywhere in the world and do analytics and so on. You also need a network, of course, to connect all the servers so they can talk to each other. And we have, first of all, in terms of security, you can configure this network in great detail. You can create a virtual private network, you can set firewall rules, and so on and so forth. It is also a highly performant network, and so it is suitable for HPC workloads. It has low latency, it has a very high reliability, and there's no oversubscription, and so on. We'll see some examples later on. Now, how do you use all this compute and storage and network? So the easiest way is that you open your web browser, your Internet Explorer, and you go to the AWS website, and there is there a list of all the services, a very long list. And for HPC, you will often use EC2 computing, S3 storage, and a few other services. And then it is point and click, and you just click, 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 and it's easy to go through all the options. Now, when you get a little bit more advanced, you'll want to use it in a different way. So first of all, there is a command line interface. So you can go in your bash shell on your laptop, and you can do anything you want to the AWS cloud. You can say, give me 5 servers, now kill 3 of them, create a file system for me, start a machine learning job. You can do all these things from the command line. And that means that you can also include all of this in your bash scripts. And you can automate everything. So creating a cluster and running a simulation could just be an automated action inside one of your scripts. You can do the same thing if you're programming in Java or Python or so. You can use an SDK and again, build all that AWS functionality straight into your program or the GUI that you're building yourself. The console gives you an overview of the costs that you've had. Here, for example, we see this user has spent about $300 so far this month. We can see that almost all of it is in EC2 computing. And here we also see that there is an alert. So you can say, actually, I want to spend only $300 per month. Whenever you reach $300, send me an email to warn me. And AWS will do that. So you always know how much you are spending on the account. Okay, so we've seen some of the building blocks, and now we are ready to put them together and assemble the HPC cluster, which is what most of you work on. It's the most basic concept in HPC. So let's get right into it. I'll give a few examples first of HPC use on AWS. We'll talk about ways to make it easy to use, and we'll talk about the performance briefly. Okay. This is one of my favorite examples. So I'm sure you've all heard of the CERN experiment in Switzerland. Yes? There we go. Thank you. A lot of the data that's generated in Switzerland comes to the United States, to Brookhaven National Lab, and they process the data there. And it's very bursty. That means that for a long time there is little data, then there is a big event in the detector, and suddenly there's a lot of data. So it's a very good type of workload for cloud. So when they had this big influx of data, they came to the cloud and they created a fleet of 60,000 cores, 60,000 compute cores. And just for a few days, for 2 or 3 days, here you see the ramp up of up to 60,000 cores. And they analyzed all the data and then took the results back out. So again, here this is kind of a weird map. But so this is supposed to be Europe. I don't know. Doesn't look like Europe to me. But let's say this is Switzerland. And the data travels to Brookhaven, and then they sent data, and they actually did it in several AWS regions across the United States. And this is again the same workflow. So this is all the data coming off of the collider. Actually, the initial data is this big. There's a data reduction step right away at the exit of the detector. They throw away 99%. But it's still big when it comes to Brookhaven. They copied all that to Amazon S3, the storage service. And at the same time, their job scheduler, HT Condor, creates EC2 instances in different AWS regions and sends them jobs. And then each of these instances pulls data from S3, processes the data, and puts the result back in S3. And then all the results are downloaded back to Brookhaven. And after 3 or 4 days when they're done, they remove all the instances and they delete everything from S3. And at that point, the amount they spent is back to $0 per day. So they were just spending money while they were doing the analysis. And it was, let's see again. So instead of 6 weeks, they were able to do the work in 10 days that way. Okay. We have a lot of examples like this. We worked with NASA on a project where they took photos of the entire Sahara Desert and then ran algorithms to calculate how much biomass is there, how many plants and shrubs and whatnot. And again, they did it on AWS, then they could get a lot of computers and get it done very quickly. We have similar examples in materials science, analyzing a lot of materials with 150,000 compute cores. And we have examples in genomics and in many other fields. Okay, in all these cases, the basic thing that you use is the cluster. So a basic cluster looks like this. This is you working on your laptop, right? You connect over the internet to AWS. Here you have the cluster head node. This is where you log in. This is where you have the job scheduler that keeps the job queue. And maybe there's also a license server or so. Then you have all the compute servers. These are the servers that actually solve the molecular dynamics, that solve the differential equations. And there is a shared file system that all these servers are reading from and writing to. And then once the work is done, you will probably store your results for the long term, again in Amazon S3 storage, where you can then pick them up again anytime. So this is what we now need to build. And there are actually a lot of pieces, a lot of Lego bricks. So if you were to do this all manually, make one server, another server, and put it together, it would take a very, very long time. Recently, I sat through a talk where, I don't know why, the speaker did just that. It took 30 minutes, and piece by piece he built all of this, and everybody was asleep after 10 minutes, of course. It was terrible. So actually, you can automate this. Like I was saying earlier, anything on AWS you can put in a script or automate. And so we're going to do the same thing. We're going to automate building a cluster so that you do it casually, like calling an Uber. Call the Uber instead of a cluster. It becomes sort of the same after a while. And I'll show you briefly 3 different tools to set up a cluster. And so important, these 3 are 80% the same. So you can choose either one. I will just present them and point out the differences. Okay. So CFN cluster is one tool developed at AWS. And it uses a template. So it's a file listing all the pieces of the cluster. And then there are just a few options in there that you have to choose. And then that big file is sent to AWS, and AWS executes and builds the cluster. For example, I often run Wharf. Anybody here run Wharf? It's for calculating the weather or the climate. Yeah. So I have a config file that tells AWS I want a C4 type servers, because these are the best for a lot of HPC work. And I want you to take this data snapshot and put it in the shared storage for the cluster, because that contains my Wharf executable and some input data sets and so on. And my cluster should be no bigger than 20 servers, because that's how much money I want to spend, basically. Okay, so I edit a little file, and then on your laptop, in the bash shell, you type CFN cluster create. And it goes to work, and 10 minutes later, your cluster is ready for you. You get an IP address, and you just SSH in there and start working. So all you had to do was type a few options in the input file. Okay. And actually, we have a tutorial for this online. If you have an AWS account, you could go and do this tutorial for yourself. When your hardware is just defined as a line in a configuration file, doing a hardware refresh gets really, really easy. This user wanted to switch from the C3 Ivy Bridge processors to Haswell processors as soon as AWS offered these. So he just edited one line in the file, rebooted the cluster, and boom, hardware refresh right there. This is much, much, much harder if you have the computers here in your data center. Clusters in the cloud are ephemeral. That means they're temporary. They don't live for a very long time. They live as long as you need them. The data is forever. So let's say that you put your input data in S3. Then next week, you have a simulation you need to run. So you create a cluster, you process the job, and once that's done, you keep the output data in S3, and the cluster is no more. You can also create clusters fit for purpose. For example, if I want to do the weather forecast, I will use a CPU cluster. I will use the fastest CPUs I can get and calculate the rainfall, let's say. But if I need to do image recognition or transform images, I would much rather use GPUs. Well, I can have both of them, depending on what I'm doing today. Clusters can also scale. Maybe one day you want a smaller cluster, the next day you want a bigger one. Again, you take the cluster that suits your purposes. And when the work is done, don't have a cluster. Why would you pay for servers that aren't doing any work? We can even have that scaling of the cluster happen automatically. AWS has something called CloudWatch. It means that at any point in time, you can poll what is the CPU utilization of my servers? How much I/O is happening from storage? So you can measure all these things, and you can have automatic reactions. For example, you can say, when all the CPUs I have are 90% busy, get me 10 more CPUs, please. And that can happen automatically. Or in the clusters, we have something that does, once there are more than 20 jobs in the job queue, create more servers. Once the job queue is empty, delete all the servers. This can happen automatically. The exact setup of your cluster could depend a little bit on what you're doing. If you're doing tightly coupled workloads, then you generally want the largest possible servers with as many cores in one box as possible. And you're going to get servers in a placement group that are close together so that the latency is low. If you have a loosely coupled job, then you can do like what CERN did and use some servers in the west coast of the US and some servers on the east coast of the US because the latency is not important. If you have an ensemble, like in weather you would often be running ensembles, say you're running 4 calculations that are similar but slightly different parameters, well, you could just get 4 clusters on AWS and run them all at the same time. I will now show you Alsace Flight, which is similar to CFN cluster, but slightly different. And I will also show you Engine Frame. Engine Frame has a slightly different approach in that it tries to really hide the cloud. So you don't see it, it's pretty, it's more user-friendly. I'll show you a slide on that in a second. Alsace Flight, like CFN cluster, also creates a cluster for you with the head nodes and the compute nodes and the auto-scaling and all that. But it's more aimed at researchers like yourself. And so one big benefit is it comes with 1,300 science libraries and codes already compiled and optimized and ready to use. So it saves you a lot of the initial setup work. And there's again a simple way to launch it. This goes from the AWS Marketplace, which is like our app store. We're not officially allowed to call it an app store, but it's an app store. Again, you put in a few parameters like how many servers you want, and you click launch, and it sets it up for you. And then once the cluster is ready, you can log in via SSH and get a nice bash shell, or you can open a virtual desktop to your head node. And again, you have all the things that you're used to, like the job schedule and so on, but you have some cloudy advantages. You only pay for what you use, you can scale it. There don't have to be job queues, because this can be just your cluster that you don't share with anybody else. So you don't have to wait in the queue. That can save you a lot of time. Also, because it's just for you, you can safely install any code you like. On the campus cluster that you share with 1,000 people, they have strict rules. You cannot just install any code, for good reasons. But here, you can install anything that you want. And as I said, they have a list of like about 1,300 codes now that are ready to use. Like here's a LAPACK library, for example, BioPerl, Python, NumPy, HDF5, a lot of things that you will probably recognize from your work. The third option, so one was CFN cluster, 2 Alsace, 3 NICE. They have something that's nicer. So there is a cluster in AWS running in the background, but you never see it. It's all happened automatically, and instead you get a web interface, and you do everything from the web browser. You say, oh, today I want to run LS-DYNA, and here's my input file, now run it for me, and it does everything for you. It's very managed, and then at some point you see, so this must have been some manufacturing or engineering workload or so. And there are even more options. So you don't just have to buy the AWS core services. There are thousands of third parties that sell some kind of higher level products on the AWS cloud. And some of those include science products like BGFS is a parallel file system. DNA Nexus has services for analyzing genomes and whatnot. So this typically costs more money, but can save you a lot of time. Okay, let's talk about performance for a minute. Now, performance is a tricky subject. People always want to know, what is the biggest you can do? You know, can you do 400,000 cores like the Cray at Maersk? You know, this is all very fun. You know, those big things get published in Nature and everybody talks about them and they win the prize. But 99% of the users, including most of you, are running small and medium-sized jobs. So whenever you program something or you build something, think about all the grad students, all the faculty, everybody, and don't think just of that one guy at MIT. That's my disclaimer. Okay, so if you want your Wharf code or Abinit code or Gaussian code to perform well on AWS, there are certain best practices that you will follow. For example, you will choose something like a C4 server type. You will set up your cluster so that the network latency is as small as possible. You will think about which MPI libraries you will use. You will probably want to turn off the hyperthreading. So there are a few best practices like this that you can follow to get good performance out of AWS. Sometimes when somebody gets horrible performance, it's because they forgot to do some of these steps. People are often worried about the network. So if you get something like a C4 server and you get a recent Linux version on top of that, then typically you will have all the drivers that can use our network to the highest possible extent. And you want to make sure you always use the placement group, which is just a way to tell AWS, please put all these servers close together so the latency stays low. Okay, so here's an example from my beloved Wharf code. So it's a benchmark where you run the weather across the continental United States. It's on a numerical grid with a grid size of 2.5 kilometers, a fairly large grid. And this here, by the way, is where I live, and this is also where it rains a lot. So you can see, this is the only lame joke in the talk, so don't worry. But so the main point here is to look at the scaling graph. So you see here, we go up to 4,600 cores, which is relatively large. And this shows you the speed up that you get. So as you go to bigger and bigger cluster sizes, the efficiency drops a little bit. But it's still quite performant. You still gain quite a bit by adding cores up to 4,600 cores. And we have examples like this for a number of codes. This is fluid dynamics, for example, where, again, we show a benchmark going up to 2,000 cores with reasonably good scaling. So again, this shows you, as you add more cores, how much faster do you get. This is, again, computational fluid dynamics. This is the airflow over a jet engine. And here, this is a little bit smaller. This is shown at 350 cores, and again shows you the speed up. Now, actually, in the literature, you will often see the speed up like this, but it's actually the turnaround time that's more interesting. How long does it take me to finish the simulation? Because that's typically what you want to know. And here, this is the most useful way to look at performance. You look at the turnaround time in hours. How many hours does it take to complete the simulation? And how much does it cost me? Of course, if you have more cores, more servers, it will cost more. And then you can decide where on this curve you want to be. Like with the weather forecasts, if I'm just optimizing some parameters in my model, and it needs to get done by the next American Meteorological Society meeting in January, do it as cheaply as possible, please, right? Because I have only $1,000. If you do it cheap, it means I can run more ensemble members and my statistics will be better. Anyway, I want to save money. Okay, so then you're going to be here and do it a little bit slower and spend less money. But if you are simulating a forest fire, and there are firefighters out there in the forests, and you need to know when the wind changes so they can get those firefighters out alive, you don't care about the cost. You just want to get it done fast. And so then you're going to choose this point of the curve. So that's how you look at these decisions. Okay. So those were the HPC basics, where we looked at how to make a cluster and work with it. Let's talk about some new ways of doing HPC. And I have a list of topics here, about 5 things that we will look at briefly. First, I want to recap just what we discussed already. So again, in the cloud, clusters are ephemeral. They're temporary. Anytime you're tired of one, you can kill it, and you can make a new one. The advantages are, first, you can script and automate everything, like building a cluster. Every user can have their own supercomputer. You don't have to wait in the queue. You have software flexibility. You can install your own application any way that you hacked it. You have hardware flexibility. You can choose the right server for the job. You can fluctuate the number of servers you use, meaning that you can calculate your science at the right dimensions, however big that molecule needs to be. You can experiment quickly, try new things, and the end result is that you're going to get your science work done faster, because all these things help you speed up. Okay, let's look at an example from astronomy. So these people at the Columbia University had a lot of astronomy data coming in from a telescope, and they had to process it within 12 hours. That were the constraints they were working under. And it turned out that if they were going to buy a cluster to put in their own data center, it was going to cost them $2 million to get a cluster that could process all that data from the telescope in 12 hours. Problem is they had $50,000. So that $2 million cluster was not going to happen. But it turned out that when they used AWS, they were actually able to do it that cheaply. And do it even faster than the 12 hours. They usually got it done in 5 or 6 hours. And the reason is that they used the spot market. And I'll explain to you in the next slide what that means. And by the way, they got some exciting discoveries out of that project as well. So what does spot mean? When you come to AWS and you use our computing services, there are a few different ways of buying computing service. The normal pay-as-you-go one is called on-demand. You say, give me the computer for 2 hours, and I pay you 2 times the hourly charge. Very easy. This is for workloads where your needs are just bursty like that. You can also do a more traditional thing and say, I will buy a server from AWS for 1 year, and then you get a discount in exchange, but you have to use it all the time. Spot is an interesting alternative. It's for work that is not urgent, and that can tolerate the occasional interruption, the occasional job crash. What does that mean? Oh, by the way, I've been telling you that you pay AWS per hour, but we just released something new. Starting 2 weeks from now, we will start billing by the second. So if you use a computer for only 3 minutes, you will pay for only 3 minutes. Something that was released just this morning, so I thought I'd show it to you. Okay. This rectangle, represents all the AWS capacity cloud, all the millions of servers that we have. And these colors are different customers using computers. And the white line, that's our safety margin. That's the unused capacity that we have at any time that nobody is using. So what do we do with that? We auction it off like eBay style in a way, right? So you can say, well, you know, AWS, I have this work here, I don't want to pay full price, but if you give me 70% discount, go ahead, give me the server and then start doing my work. And because we are so massive, even this little white area is still very, very big, is still much bigger than the total compute capacity that most organizations have. And so you set your price, you say, well, normally this big server would cost $1.5 per hour, I'm willing to pay 40 cents. And then we tell you, actually, you're in luck, we have spare capacity now, and it's only 28 cents. So you pay 28 cents per hour for that capacity. Very popular with scientists, because scientists tend to be very budget conscious. Okay, so there's sort of a supply and demand, you set your price, and whenever we have compute capacity cheap enough, we give it to you. there's one downside. When full price customers want that capacity, we can take it away from you again. And then you have 2 minutes to stop your work. Like you checkpoint the code, you save the state of the application. Now, it doesn't actually happen often. Remember that the slide with the Fermilab and the 60,000 cores? They lost less than 1% of their jobs. They did everything on spot as cheap as they could. They set very low price, and they lost less than 1% of their jobs. So it works fairly well. But you have to be aware there could be an interruption. So here you see the fluctuation of the price over the days. And this here is up here would be the full price. So it's often a lot cheaper. Discounts of 50 to 90% are fairly common. And this can be done at a massive scale. I'm aware of a recent research initiative, a science initiative that used a 1 million core compute fleet using spot instances. So, big. And all the tools that we looked at before, like CFN cluster and Os's Flight, can do this for you automatically. Just bidding on the spot market and taking care of it. So look into it if you have budget concerns. Okay. Let's draw a bit of a timeline here. So it used to be that all HPC hardware was physical. It was the computer that was sitting in the office next to yours. Then we started virtualizing. For example, servers, virtual servers in the AWS cloud. And then recently, I'm sure you know, people have been Dockerizing just everything. Everything is being turned into containers and microservices because it's very versatile. A container has just your application inside, the library dependencies, but nothing else. And so you pick it up and you can put it in the Windows, in the Linux, in a different type of Linux, and it will run anywhere. So people love it for that reason. And the next step is actually where you go to serverless computing, where you don't even worry about the container anymore, but you just tell, for example, AWS, here's my Python code, run it. I don't care how you figure it out. Right? And so it becomes easier and easier and more granular as you go across this line. Let's see, if you work with containers, then we have a new service called AWS Batch. And it's the only AWS service with a sensible name because it actually does have batch computing. So you can just say, here is my job, my molecular dynamics job, in a Docker container. It optimizes the structure of some molecule. And actually, I have 10,000 of these jobs. Here's 10,000 input files, each with a different molecule. And so you need to run this job 10,000 times. And so the Docker container needs 2 gigabytes of RAM and give it 4 hours maximum runtime. Okay. And then you just drop all your jobs in a queue, and you can stop worrying about it there. So you don't have to provision servers to actually power those computations. That's all managed by the AWS Batch service. So you just define the job, and that's all you have to do. And it has a lot of advanced features like job dependencies, start job 2 after job 1 completes, or retries if job 1 crashes for whatever reason, try it again, and so on and so forth. For example, we have a lot of people using this in genomics. Let's say that you have some DNA scan or so, and you upload it into AWS storage in an S3 directory. And then you go away, you go have coffee. Okay. In the meantime, what happens? There is a trigger function defined on the storage. Every time a new file of a certain type comes in, it automatically takes some actions. It automatically defines a batch job and throws your file in the batch job queue. Batch automatically runs the compute step, sequences the genome, and puts the output back in your long-term storage. All you had to do was upload your file. Everything else happened automatically, right? So you can easily build systems like this. You spend a few days on AWS, you'll be able to build things like this. If we look inside a little bit, again, the same example. We drop the file in storage. There is something called a lambda function here, which is a trigger. It puts a job in a queue. There is something monitoring that queue. When the queue gets bigger, it says, oh, let's get some servers here to process the work. And then it runs the container and the job and puts the output back where you wanted it. But so all this happens automatically in the background. You don't have to see it. Okay, so that was a quick note on computers. That was a quick note on containers and batch computing. Let's talk about serverless computing now. We have a new service called AWS Lambda. And Lambda is a service for software functions, like a Python function, to be deployed in the cloud natively. And all the infrastructure underneath, the hardware, the operating system, and the software environment, is managed by AWS. And because we know very well how to do this, this will be a very reliable and a very fast scaling environment. So all you do is you write the Python code, you tell us which Python libraries it needs, and you give us that. And then we run it for you, either when you say it, or automatically every time an input file is uploaded. You can define the events in various ways. I'll show you two examples, one from genomics and another one from machine learning. So we work with a lab at Berkeley called WISE Lab, and they realized that these functions, these Lambda functions, are really powerful. Each of them is quite small, but you can create thousands of them really, really quickly. So it's like instead of the old HPC cluster is like an elephant, and this is like a swarm of bees, right? And so they wrote a Python library that makes it really easy for a user to just say, here's my function, and run it on 2,000 of these little function workers. And these can scale up in just a few seconds, much faster than you could scale up a server-based cluster. And it turns out that you can actually get to HPC levels using all these little Python function executions. For example, they showed here on some benchmark, they performed at 45 teraflops of compute using 3,000 of these Lambda workers. And they were able to process input data at a rate of 80 gigabytes per second. So a very, very high throughput rate. So using these tiny building blocks, you can actually build a high-performance system in a very flexible way. Here's another example from genomics. So this is from an Australian research agency, CSIRO, and they had a workload where you give them the genomic data from a patient, and then you need that data to be scanned to identify certain gene sites and pick the best ones to do certain work on. Now, there were two things that made this difficult. First of all, that job could take 1 second or it could take 5 minutes, just depending on how complicated the genes are. So it's very unpredictable. And second, this has to happen in real time, so they need to get the results back immediately. They can't wait 10 minutes or half an hour. It's very hard to accommodate this if you have servers. Because either you don't have enough servers and now you have to wait 5 minutes just for the new servers to arrive. You don't have that much time. Or you have a lot of servers that are sitting idle most of the time, and then you're wasting 90% of your money. So what they did is they chopped up their workload and encapsulated it in Lambda functions. And the Lambda functions can scale up to any number in a few seconds. And so that way they were able to create an application that had a predictable runtime. It always returns the results within a few minutes, no matter how complicated it is, and no matter whether they send one job to AWS or they send 1,000 at the same time. The system responds with the same speed. And cherry on top of the cake, it took them only a few weeks to change from a server-based architecture to a serverless architecture. And this is really one of my favorite examples to talk about, because I think this is what the future will look like. We're going to see more and more people inventing new things or following new ways, breaking up their applications and finding clever ways to do it. Like the old NPI model is sort of reaching its limits in some ways. All right. What should be finished by 20 minutes. Okay, thank you. So a lot of people these days like to do accelerated computing using GPUs or FPGAs. And this is the way to understand it. A CPU is like a plane. It's really fast. It can go anywhere you want, but it takes only a few passengers, and it burns a lot of jet fuel. Accelerators are like a train. They're also very fast, but they always go to the same destination. They're not flexible. But they can carry a lot of passengers, high throughput, and they use much less energy. That's the conceptual way of understanding it. GPUs have a lot of cores, and they're set up to do the same thing very many times. Single instruction, multiple data. FPGAs, on the other hand, are more complex. They have millions of individual compute cells, and they can be programmed in a more flexible way. The downside of FPGAs is they're very new and very difficult to program. Just like GPU used to be 10 years ago, right? 10 years ago, that was a nightmare programming GPU. FPGAs are like that today. AWS offers both. So we have GPU instances that have up to 16K80 GPUs. Those are good for numerical double precision work. For example, the Swiss Meteo service uses the same GPUs to calculate the weather for Switzerland every day. Our FPGA instances, I think we may be the only cloud that offers those at this point in time. So those are used, for example, in genomics to speed up certain workloads by a huge factor. Okay. And then I'm going to skip a few slides just to catch up on time a little bit. I want to say a few things about machine learning. Apologize for the font here. So machine learning is, of course, the biggest, hottest thing these days. Everything has to be, you have to call everything artificial intelligence today if you want to get funding, right? Anyway, so you can do this on different levels. So you can just come to AWS and get an EC2 compute instance and then program and build your own machine learning system on this. Very flexible, but a lot of work. Or you can use one of the popular machine learning frameworks. So these are basically libraries that contain a lot of powerful machine learning models. So, and AWS provides you with a machine image. You can just say, AWS, give me an instance with all the machine learning libraries. It will give you that. And then you stage your data, your training data, you train the model, and then you start making predictions. A lot of people like to do this through like Jupyter notebooks these days. So a lot of people these days are using Jupyter notebooks, and then there are AWS instances in the background doing the work, but you have that nice Python interface. And at the top end, we also have some fully managed machine learning services, where you just, in the browser point and click, you dump the data and it starts making predictions. These are the easiest to use, but also the most limited because they have a smaller set of simpler models. And I'm going to go through this. I'm going to skip a few slides because we have to catch up a few minutes. And I know that you will hear more about machine learning later today. But we also, you can do this in clusters. For example, here you see an example. We have, I think, a cluster of 16 GPU instances with 16 GPU cards each. Why would you do that? Well, machine learning is slow. It takes a long time to train your model and all the training data. So if you can do it in parallel on a cluster, you get a big speed up. In this case, it was 110 times faster than if you did it on just a single GPU. So you can catch up and start making predictions much faster. Okay. Collaboration. Whole new subject. So collaboration, of course, is the key to doing science. Almost nobody today, there are no Einsteins anymore. It's almost impossible to do something by yourself, right? So you work in collaboration. And also, you always want to make sure your work has impact. If you write code, you want other people to use it. If you have data, you want other people to help discover all the science out of that data. One, because it's better for science in the world, and two, because the people who pay your grants want to see that impact, of course. The cloud is actually a fantastic platform for collaboration. And there are a lot of reasons for that. The first is that we really understand security. In a traditional environment, it's often really black or white. Either you're outside, you can't see any data, you can do nothing. Or you're inside and you have the root password and you can destroy the world, right? And so the cloud is really built from the ground up with very sophisticated, very nuanced security controls. Every aspect of your workflow, every data file you upload, you can set very detailed permissions. So that trade-off between sharing and security is a lot less painful in the cloud. And you can do it in seconds. You don't have to wait for your campus administrator to approve and that. Also, we have servers all over the world. So if you have collaborators in Japan, yeah, well, you know what? We have infrastructure in Japan. If you put data in your AWS account, your collaborators can access that data if you give them permission. And then they can run all the analysis jobs in their own AWS account. So it is not sitting in the queue of your cluster. It is not going to your build. It is completely separate, but they can do it on your data. The same with your applications. If you have a molecular dynamics code and you share it with the world, anybody can use that in their own AWS accounts. And because you have that near infinite pool of EC2 resources sitting right there, next to the S3 storage, it's never a problem of capacity. Right now, we still have a stupid situation in many fields, where there is 100 terabytes data sets of the global weather model. And everybody at every university goes and downloads that copy and has to wait 3 weeks for it to download and then buy hard disks to store it, and this is just ridiculous. If you put one authoritative data set in Amazon S3, everybody can go and do their compute on it. Or everybody can still download it from there if you want. And just to be very clear about one thing, anything you put in the cloud, you are still the owner. You never lose your intellectual property, you have 100% ownership, and you retain data sovereignty. If you put your data in the Germany AWS region, we will never move that to Japan or France without you explicitly saying so. For some people, this is very important. If you work on projects for the government, this could be very important. If you work with personal health information, this could be very important. Right? Okay. We already talked about that. You can share applications in many ways. You could give people a virtual machine image with your science code. You could give them a Docker or a Lambda function. Or you could even publish your app in your app store. You can charge it, you can put it there as a free app, but it's a nice way to make it visible to the world. For sharing data, actually, we think sharing data in the cloud is a good solution to the big data problem. And to give the good example, we host a small number of important data sets for free for the whole world to use. And this is called the Open Dataset Program. Some of these data sets are in genomics, for example, the Cancer Genome Atlas, but a lot of them are in earth science. And we have a website called Earth on AWS that has a lot of 3D pictures. For example, we host NextRad radar observation data there. And I'm going to skip over some of the details here, but this is what happens. Here we're sitting on the US government servers. And this year we added a copy on AWS. And so the usage almost tripled. Why? Not because people are in love with Amazon, not because they love Amazon Prime shipping, but just because it became more accessible and much easier to use. And this is the golden rule in science. Make your stuff easy to use, and people will use it. Another example is Landsat. So satellites are taking photos of the Earth all the time. And so in different wavelengths, so you get photos like this. So we store that full archive on AWS. And that gets hit with roughly 1 billion requests a year. Again, if you build it, they will come. Finally, so I wasn't kidding when I said that we invest more in security than anybody else. And so we have a lot of independent third-party security certifications. If you work with health information, for example, you may need to be HIPAA compliant. If you were in the US and you worked for defense, you would want to be ITAR compliant. And there's probably some 50 or so or 60 of these certifications that we currently have. You can keep logs of absolutely everything that happens to the data that you store in AWS. So you can make it very, very secure. And some scientists have said that actually it's more secure in the cloud than what they do themselves. Not here, I'm sure. And again, when you put data in S3, it's not just storage. You have machine learning services right around the corner. You have infinite compute capacity for it. You have database services. You have services like we have Athena, where you define your SQL query and run it on a data set without having to load it into servers or provisioning servers. You can immediately make it available for the whole world to see. So there's a lot of benefits that come with being there. Okay, now I have only 10 minutes left. And these are maybe my most important slides, so everybody perk up again. Almost time for the coffee break, I hope. So let's talk a bit about the ways that we are specifically looking at the research community. Because on the one hand, you benefit from us building infrastructure for the whole world. Again, our size brings you a lot of benefits. But on the other hand, you are academics. Something is special about you and your culture, and so you want to know what we're doing about that. So first of all, we learned that researchers often find it difficult to start on AWS because they say, well, where do I start? There is so much, right? And so one thing we have done is we've written a handbook, the researcher's handbook. It's like the missing manual for the cloud. And it takes you by the hand, and it says, look, here's the reason to work in the cloud. Here is how you set up your account. This is how you make it secure. Here are the basic compute and storage services that you should learn about. And people are generally quite happy to read this handbook and learn that way, rather than having to learn from the AWS website. We will be publishing a new version of this in a few weeks. Here's a table of contents. So for example, configure the AWS account, how to budget, make sure you don't spend more than you want, how to work with data or with compute, how do you do clusters in HPC, how do you use Jupyter notebooks. Okay. All these topics take about 100 pages. And then there is another 100 pages that's all presentations from third parties, other companies that offer scientific codes or scientific products on AWS that you might be interested in. The handbook comes with a bunch of science use cases. For example, here's that genomics example that we talked about just a few minutes ago. And it has lots of links to tutorials and blog posts and background information for you, so you can sort of learn by example. And then, like I said, it has, for example, we looked at also slide cluster, so that's described in the back of the handbook. Okay. Second topic, we know that researchers hate paying for data downloads. In the cloud, everything is pay as you use, so when you download 100 gigabytes of data, there will be a cost for that. It's usually a small cost, but researchers don't like it because they're not used to this. In the traditional computing centers, this is not a separate cost, and they say, oh my God, I have to be able to predict my cost, so please do something about this. So we have a special program called the Global Data Egress Waiver that any researcher can join, and it means that we will take those data download expenses off of your bill, up to a limit, but it's a generous limit. And part of that is taking advantage of peering with research and education networks, which probably all of your universities are linked to one of these networks. We have a Cloud Credits for Research program. So this is it's a program that gives some people free AWS credits. And it's particularly for people that want to develop things like community tools. So if you have something you want to publish in AWS and you need a little bit of help getting it ready, we are there to help you. Carlos here would be the right person to assist you with that. Now we know that the funding agencies actually rule us all, right? They're the boss in the end because they control the money. And so we are working with the research funding agencies to become more aware of cloud, understand when should researchers have the option to choose cloud. Researchers always choose what's best for them, right? Whether it is buy your own service or go to the cloud. but you should have the choice. So we are working with the research funding agencies to give you the choice. And for example, in the US with the National Science Foundation, we did a $27 million sort of joint call where they paid salaries and cloud providers provided credits. And we're trying to open up the regular review process to make sure that you can all use cloud when you want to. Oops. We have a program for students, so if any of you are classroom teachers or TAs, you can sign up for AWS Educate and get free credits, so you can teach and your students can do, for example, HPC work in the cloud during class. It's very popular. We have hundreds of thousands of people using this, so you can sign up too. We have a lot of very detailed tools to control your budget, including something that we program for researchers, something to shut down all your servers if your spend reaches a certain threshold. A lot of researchers have asked us for that. There are also tools for central campus to manage all the accounts on the campus and make sure that you keep your compliance. Is academic overhead a thing in Colombia? Yes? Okay. So in the US we have this problem that if you get a $100,000 research grant, the university says, yeah, please give $40,000 to us to pay the salaries of the administrative staff. And now, we need administrative staff, okay? I like the administrative staff. But it's a little bit silly to charge the overhead on cloud, because the cloud does all the administration of the resources for you, right? And so we're making some progress with some institutions that now say, okay, if you spend money on cloud, you don't have to pay overhead on the cloud spending. Oh God, I have to talk about this at least 1 minute. So we work with the WISE lab. It's this awesome, huge machine learning lab at UC Berkeley. And the past 5 years, they were called AMP Lab, and they built Apache Spark. Any of you use Apache Spark? So it's used all over the world. So these guys built that. That was a collaboration with AWS, where we actually sponsored the research activity, and that whole thing was developed on AWS infrastructure, natively on AWS. And right now they're in a second 5-year phase called RISE Lab. And they're building another general purpose machine learning stack. But what is the machine learning of the future? It is one, it has to be real time. Predictions have to come back in 10 milliseconds. Because the predictions are going to be used by systems like drones and self-driving cars, they can't wait a minute for a calculation, you need it now. Second, the models have to become real time. So the data sets are going to be updated in real time and you have to retrain your model continuously. And so they're building a new set to do that, and exciting things will come from there in the next couple of years. So AWS occasionally sponsors real collaborations like this. Okay, last slide. Thank you very much. We will be here today. If you have some time tonight and you're interested, sign up for the Research Cloud program, get the handbook, and if you feel adventurous, since you're interested in HPC, try to follow also slide tutorial. For this you will need an AWS account. If you have an AWS account, this is a fun way to learn about HPC on AWS. Thank you.
Muchas gracias. Como Kevin lo había comentado, mi nombre es Carlos González, yo soy el responsable de AWS Sector Público para Colombia y Perú. Vamos a estar aquí en una salita durante todo el día, en una salita que se llama Access Street, con el objetivo de tener, digamos, follow-ups, reuniones con ustedes en áreas, obviamente, de tratar de entender un poco más en detalle los temas que se tocaron acá. Les informo también el tema de Research Grants. La semana pasada, por darles un ejemplo, aprobamos uno de $11,000 más o menos para universidades mundiales para un desarrollo con la IDEAM en el desarrollo de cube de información de espacial. Así que, digamos, estamos constantemente dando grant, no tenemos límite realmente. Así que, bueno, si quieren más información, vamos a estar ahí. Y también ahí les puedo dar todos mis datos de contacto. Pero muchas gracias por la invitación. Espero que haya sido la presentación de valor. Thank you, Kevin.
Muchísimas gracias al doctor Jorissen, a Carlos, a todo el equipo de Amazon Web Services. Thank you very much. We really want to thank you, Dr. Jorissen, Carlos. Thank you to all Amazon team present here. Thank you very much.
Happy to be here.
Creo que tenemos algún tiempo para preguntas, entonces los interesados pueden preguntar en español para utilizar la traducción, o si quieren preguntar directamente en inglés no hay ningún problema. Una pregunta, estudiantes, el ingeniero y luego.
I think that is possible that Jorissen mean, okay? We are very. We had some question about the data transfer. For example, in Colombia, the most important client for this type of solution is the government. But the government had some question about the security, the information about our people, and the other is what about the cost of transfer information from on-premise solution like a data center of government to Amazon data center?
Okay.
Especially for a country like Colombia that we had some limitation in a bandwidth, etc. What is the option in Amazon Cloud for that?
Yeah, so uploading data to Amazon is free. That does not cost anything. For downloading data, there is a cost, although as a researcher, and also most government agencies could qualify for that special program where that cost is waived. So that's also potentially free for you. In terms of security, the best practice is that you use encryption, encrypt your data at rest and in flight, and then you can sleep soundly, no matter what happens. Nobody is stealing your secrets. In terms of the bandwidth and the speed, that will depend largely on your side of the problem. Amazon has a very strong backbone. We have a lot of capacity. So usually when customers see a bottleneck, it's usually closer to the customer. I try very hard to create peering with all the NREN, is that a word here in Spanish, where we say that, the National Research Education Network, because those are special high-performance networks that are dedicated to the universities and whatnot. I'm not sure if we peer with any in Colombia, but it is something that we could follow up on. And if there is a demand for this, we could look into potentially creating a new peering point or adding capacity. Sure.
So the advantages of cloud computing are undeniable, right? And we see a lot of people moving their computations and their simulations to the cloud. There may be some organization that may be hesitant to do it because they worry about their intellectual property, the data breaches and all the hacking that is being taking place. Like last week or 2 weeks ago, we had the big one that happened with Equifax. And then the organization may have some internal policies that prevent them from having their data in an external site. And so I wonder what the message is from you guys to organizations like that.
Yeah. So first of all, Equifax got hacked. Nobody hacked Amazon. So usually in those situations, what you need to do is you need to get all the folks in an organization that are responsible for security. Because they're probably good people, they just feel responsible. And you get them in a room, and we come in and talk about what we do for security, all the compliance programs that we have, all the security features that we offer. And in a lot of cases, that ends up convincing those people that they can do their job. Because they're doing their job, they have to guarantee to their users that everything will stay safe. Usually we can talk to them and help them make that leap.
El comentario con respecto a eso es sobre, obviamente, lo limitante de la protección de la información, datos personales. Hemos venido, obviamente, trabajando con MINTIC y también con Colombia Coproficiente en introducir estas nuevas tecnologías. No es fácil cambiar 40 o 50 años de modelo tradicional de compra de bioadquisición o manejo de cómputo de hardware y software, propiedad intelectual, movernos a un modelo de servicio, ¿no? Entonces el MINTIC ha estado muy proactivo en esto últimamente. De hecho, emitió un documento de uso de cloud en el gobierno, en el Estado colombiano. El presidente de Santos anunció en el ANDICOM, como ustedes saben, los servicios digitales ciudadanos, carpeta digital para los ciudadanos, y él mismo decía: esto va a correr en el cloud, o sea, no hay forma de que esto pueda correr en un data center. Entonces, sí, los datos, digamos, el cambio viene obviamente lento, pero el gobierno obviamente actualizando y se está moviendo hacia allá. Hay una disposición muy fuerte también de la SIC de integrar a Estados Unidos obviamente como un país donde se puede transferir y transmitir información, datos personales obviamente de forma segura. Así que hemos venido, hay que cambiar 30, 40, 50 años obviamente el modelo tradicional, pero obviamente los cambios están dando.
¿Alguna otra pregunta? ¿Any other question?
Is there any relationship between Amazon model and MapReduce program model?
Well, so we offer MapReduce service, right? So EMR, Elastic MapReduce, so we offer a fully managed MapReduce. So if you want to do a MapReduce job on AWS, you could do two things. You could go to EC2, get some compute servers, and do everything yourself. Or you can use our managed service, where we take care of provisioning and managing all the hardware for you. Which is, for most people, I think, the better way to go.
Okay. Bueno, entonces, si no hay más preguntas, damos por finalizada esta primera conferencia, no sin antes agradecer una vez más la presencia del doctor Jorissen en nuestro evento y las gestiones de Carlos y su equipo de trabajo. If no more questions, thank you very much again. Thank you very much.
And you have my email address, so you can follow up with us in the future.
Thank you. Invitamos a todos nuestros asistentes a tomar un refrigerio en las afueras del auditorio. Continuaremos con nuestra agenda en 10 minutos con el seminario Acelerando Aplicaciones con MATLAB. A continuación, en este mismo espacio, con la conferencia Deep Learning a New Computing Model a las 11:30 en la sala de videoconferencias de la Facultad de Ingeniería, localizada en el piso de arriba. Muchas gracias.
Su espacio doctorado y ellos ven cursos en teoría.
Sí, algunos publican solo en plataformas universidades,
En YouTube en este momento ya hubo una transmisión.